Welcome back to the channel, folks. This is a video that I've been wanting to get done for quite a bit of time and just haven't really been able to get around to it. But I wanted to talk about specifically the huge amount of power that modern graphics cards seem to consume. It seems every single year there is a step up in the amount of power needed to actually run these platforms, and quite frankly, it's just getting a little bit absurd. Given that, for example, the 4090 cards, especially a lot of the ones that are actually available, meaning not the reference ones, are currently consuming anywhere in the neighborhood of 500 to, in some cases, north of 600 watts at their peak, sometimes peaking a little bit higher, going closer to about 800 watts in some cases. And I think it has just gotten to a point where, at some instance in the future, it is just not going to be feasible, at least on the sockets here in the United States at 110 or 120 volts, where we have a maximum of potentially 1300 watts of power that you could pull off of a single socket before essentially it would just trip your breaker. Now, you can certainly upgrade your breakers in the house to make it be able to withstand a little bit more, but in reality, that is going to be the absolute maximum, and it is the safest legal allowed, I believe, currently federally in the United States, which means the chances are, if you're going to be running future PCs, you have a couple of options. Normally, in cases like these, you would probably end up having to get a second power supply to go into your computer, because otherwise you would have to upgrade to one of the, let's say, 1400, 1500, 1600, whatever watt power supplies that are then able to run off of 220. But of course, that would then also require you to get a 220 volt socket in your house. And, well, somebody like me who happens to live in an apartment, that's not exactly feasible. I'm not going to ask my landlord to place a 220 volt socket in this area. It's just not going to happen. And I think for a lot of people that are also in their homes, upgrading their electrical panel to be able to support this is also quite a bit of money. Usually there's a lot of permits involved. You have to go through the city, you have to have an electrician come out, etc., etc., etc. It's really expensive, it's a huge headache, but I have a feeling that that's going to be more or less the way things are going to end up going, especially if NVIDIA continues doing what they do, which is essentially pushing the cost onto the consumers, essentially saying, hey, Moore's Law is dead, which means now everybody's going to have to pay higher prices because continuing to develop the nodes costs a lot of money. Now, this is all fun and, understandable in a lot of ways, because you have to keep dancing around this problem. We can't keep shrinking the nodes down continuously, because eventually, once we get down to, let's say, less than the width of an atom, you start having a lot of different interference problems, and already that's causing issues on some of the smaller nodes, such as the 3 and 2 nanometer nodes that are going to be coming next, past this sort of current 5 nanometer node, which in reality they're still really 7 nanometer nodes, just sort of slightly shrunk down again, but that's a story for another video entirely. However, with every single node shrink that's been happening, or rather the shrink of the manufacturing process, what we've been seeing is that even though the cards are technically more efficient, they are instead actually pushing these power limits higher, because now, due to them producing lower heat at the same consumption, they can push the clocks further to get more performance. Now, on the one hand, this is great, because if you do end up undervolting the card, it actually ends up outperforming its predecessor by quite a fair margin without actually consuming quite the ridiculous amount of power, potentially, or consuming the same amount of power but still outperforming its predecessor. But at the same time, due to the fact that none of these cards come with this undervolt from the factory, this means that this is something that you as the consumer have to do. And I think that going into the future, unless again we're going with some sort of double PSU inside of your case, or one of those modern PSUs that have 2 redundant units essentially in them, the only other way that you're really going to be able to avoid this is by doing something with the GPU, switching from the silicon substrate to something like graphene, again to help reduce, for one, sort of the amount of heat that is escaping in the system in terms of inefficiency, or you're going to have to move from the currently copper traces to perhaps some sort of a superconductor, again to relieve the amount of heat lost due to the resistance in that particular material, and again changing that substrate to help facilitate that sort of changeover even more frequently. But at the same time, you're looking at changing all of the tooling in a lot of the factories to be able to accommodate these processes so that you can make the change happen. But I think that the change needs to happen because shrinking the nodes is simply not going to be a thing anymore, probably within the next 10 years, unless there's some big material science breakthrough, again, that allows, us to either have a new type of material used for the transistors, or there's something else that is being developed to allow them to stack more of these into a smaller space. At this point, FinFET is already behind us. We've already moved on from that. Stacking transistors on top of one another has been a thing, but again, you can only go vertically so high before you end up introducing other problems, which means at the end of the day, I think that a change from silicon to something else, maybe graphene, maybe something else entirely, is absolutely the way forward, just so that we can continue keeping the power outputs, essentially increasing, or perhaps maintaining them, but while at the same time reducing power consumption as it has gotten completely out of hand. Now, there are obviously ways that we can also currently go with a sort of more direct cooling of these chipsets internally, perhaps. There's been research being done on putting microchannels, so something very similar to what you would see on a water block, where they cut those straight lines across on top of the actual copper to allow it to have higher surface area so that more water can flow across that, and again provide you a better amount of cooling, because more surface area allows you to dissipate heat a lot better, more efficiently. Now, the issue here is that, of course, that means that unless you water cool those components, and water cooling being something expensive and not really something that you could really put, for example, into a console safely, again, without potentially going into some sort of a closed loop system that is entirely based on some sort of a working fluid. But again, even these pumpless systems have a tendency to still have evaporation over time. Maybe that's not something that's reasonable over the console's lifetime of potentially, let's say, 5 to 7 years, where this system probably will keep on working. But again, that also requires an entire rethink of how all of these systems would be packaged. And for example, in a PC, where there are different types of motherboards, different layouts, it's not really feasible to go with this sort of closed loop cooling system unless you're able to develop a system that's not reliant on gravity to move these things. And even though we've gotten to a stage where essentially capillary action allows us to avoid issues with gravity getting in the way of, depending on how the system is mounted, ultimately I think that this is not something that's going to be 100% feasible across the entire spectrum of devices. While on the server side, where most of these are now being liquid cooled or potentially immersion cooled, on the desktop and consumer side, it's not really super feasible. But if you're going to start stacking chips on top of one another, doing some sort of microfin cooling is probably the only way you're going to be able to get efficient cooling across all of these chips, across all the cores, transistors, etc. But that also requires a rethink of how these devices are essentially packaged internally, because obviously over time, even if you coat them with a conformal polymer coating, the water or whatever fluid that's going in there is likely to wash that away as the cycles continue, and that also means that eventually you're going to end up introducing some sort of a short in the system that will cause it to fail. That also causes even more problems, because then you can't really justifiably ship these out to consumers, because the amount of life on that chip will continue to degrade. Now, one team has come up with a solution for this specifically, where they actually basically coat the entire chip with a sort of surface level coating of copper, essentially coating every single component on there with a copper substrate of some kind that allows them to cool all sides of the chip uniformly. But again, they do use the conformal coating on the inside to not have any kind of shorts, but that also means an entire rethink to how you manufacture these chips. And obviously copper, while being cheaper than a lot of the other conducting metals, it is still not exactly the cheapest thing out there, and there's obviously not that much of it to go around, with the commodity price of copper nowadays being pretty much at an ultimate high. that also means you're going to be paying a lot more for chips, and potentially it pushes out production schedules quite a bit. But with that said, at a certain point you have to go with some sort of additional or modern cooling method to allow these chips to continue to push the clocks higher while not being as hard on the consumer wallet at the end of the day. And potentially with this sort of method, you may be able to have cooling on both sides of the chip. So potentially we'll end up having motherboards where you have either CPU coolers that are air cooled on both sides of the board, or you have two water blocks sandwiching this chip, allowing it to receive cooling from multiple areas. Or again, it could end up being that we use some sort of microchannel cooling where you have essentially ports on each side of the chip, and then that runs water across the length of the entire chip, and therefore cooling all of it, again potentially with this copper sort of coating being all over the internal components, as to allow it to essentially act as a thermal interface material for literally the entirety of this chip. And in essence, this would allow this sort of next gen level of cooling that is significantly more efficient than what we have right now, where in essence you have to have not only a heat spreader on top of the chip, but you also have an additional layer of cooling that has to be applied on top of that in the form of either a heatsink or a water block, again reducing the efficiency of the whole system, because you now have to go through two separate setups before you actually get to cooling the chip, meaning that you're increasing the distance at which the actual cooling is applied to the chip itself, leading to inefficiencies in how the chip performs, and obviously also limiting the cooling that you're able to get out of it. But obviously from the hardware perspective, there's only so much that can be done, and I think it's sort of unreasonable to expect that all of a sudden we're going to get to a stage where all of these chips are being cooled this way, or that all the manufacturers jump on board with this particular bandwagon and just decide that this is the path forward from now on. I think that more realistically, what we'll end up seeing is more algorithms that are being developed for neural upscaling. Now, hardware upscalers, something like this PhotoFast unit that I've reviewed recently, are another potential way forward, where if you don't necessarily have the most powerful graphics card, you can still push your game. So for example, you can game at 1080p, but then output in 4K using this unit to your monitor without having to consume the ridiculous levels of power it would otherwise be to run that game at your 60, 120, whatever frame rate you decide to be at. So potentially these little units may be one path forward to reduce overall power usage, because they essentially allow you to kind of cheat to get that high resolution without necessarily spending the extra power and producing all of that extra heat that would normally be lost, because these devices obviously are not the most efficient. But I think as far as the hardware side of things goes, it's not highly likely that there will be that many more developments of these types of devices, simply because things like DLSS and neural network upscaling are really the big thing now, meaning you're taking a lower input and then you're essentially using a convolutional method to be able to determine either a next frame that you can add in, as is the case with DLSS 3, or you're enriching the information that's already available to you by using the colors of the pixels, the Z buffer, or the depth, and then also enriching the data that the neural network receives by inputting motion vectors that essentially help you predict the next frame, but they also help you predict essentially where things are going to potentially move in the next frame. And obviously a lot of this probably, I'm guessing, even though I have not studied this clearly, is something to do with gait recognition. Perhaps they recognize how characters are likely to move, and then they add that layer into this network to be able to predict character maneuvering around the screen in a way that would make the most sense and help determine how they can render these next frames without actually having to do that render, meaning that you're saving yourself precious time computing all of the extra pixels on the screen. Instead, you can just take a shortcut and essentially predetermine some of these, allowing you to push frame rates higher while also upscaling from a much lower basically internal resolution. So you could take something that is running at 720p and potentially be outputting in 4K or perhaps even higher, because as one of the Oculus papers that I'll link in the video description below states, they are actually able to get the performance that is much better than DLSS 2 at the time of the writing of this article, they were saying that DLSS is able to really perform well at the 2x level. So you're talking going from 1080p to, let's say, 4K. That seems to do reasonably okay with DLSS, but anything beyond that, it tends to struggle a little bit in terms of getting a proper kind of frame rate and also making sure that the actual imagery looks really good. Now, with the Oculus paper, they're claiming that they can do 16x and also not depend on internal DLSS hardware. And in the case of DLSS 3, we have these optical flow accelerators, which I'm not entirely familiar with, but they say that that is more or less necessary to drive DLSS 3 properly, even though it's been shown that you can run DLSS 3 on older cards by just changing some config files in DLSS and allowing it to run, but I don't know how well the frame prediction would work at that point. But the idea here is that more than likely the VR technologies that have been driving the frame rates and the sort of frame prediction, asynchronous warp, all of that stuff is probably going to make it to the Pancake or 2D games at some point down the road, because ultimately we need a higher level of upscaling if we're going to continue to see improvements and also be able to render at these ridiculous new resolutions such as 8K, which even on the most current 4090 is simply not achievable in a lot of games without DLSS. I mean, you're talking about potentially putting out games that are just unplayable on modern hardware unless you use some sort of upscaling method. And I think that using these neural nets to upscale is potentially the solution that does not even involve you having to get any kind of a new power supply, but we'll see what ends up happening with this. I'm really curious and excited for this next stage, but also I'm kind of curious to see if Oculus or Meta decide to actually fully open source their method, because they're saying that their particular solution can actually integrate into a lot of game engines that already exist without requiring, again, that dedicated hardware that you would normally need from the NVIDIA side of things, for example, to be able to run DLSS 3, nor does it rely on any sort of AI accelerated cores, for example, something that would most likely be driving FSR 3 on the AMD side, as they did say that they have released additional accelerator cores on the 7000 series GPUs, but NVIDIA states that this can run pretty much agnostic of any kind of hardware you have and provide you a massive increase in resolution from the original input image, as well as good quality, again, just based on the prediction that they're able to do. And potentially this means that devices like the next-gen Switch could leverage some of this technology to, again, not have to have additional cores on board, because anytime that you introduce additional components, that introduces complexity and introduces cost, but it also introduces additional heat in the system. And if you can get away without having those additional compute units on the die, that means that you're effectively making the unit run more efficiently, therefore consuming less power. But I want to know what you guys think about this. What do you think is the next step in our evolution of computing for graphics cards and also potentially CPUs that may involve us using less power? Go ahead and comment in the video below, and I'll see you all in the next one.